get your PhD, you're supposed to become an expert in something that nobody else is an expert in. And I got my expertise in rotting fish.
There you go.
I was interested in the fossil fish in the Green River Formation in Wyoming. If you've ever been to a rock shop, you've probably seen some of those fish in there. They're numerous, and they sell them worldwide. Just beautiful fish. But I wanted to understand the processes that make those fossil fish and how come they're so well preserved. And so not only did I do a couple quarries in Wyoming to collect the fish and study the fish there, but I did a bunch of experiments in my lab back at Cedarville with real fish, watching how they rot and decay. And I actually learned a lot. One of the things I learned right away is this lab was right outside of my office, and you actually had to walk through the lab to get to my office. And I noticed I could cut down on student traffic a lot running these experiments. They did stink, yeah, they did stink. But what I found wasn't too surprising. The fish, no matter what the conditions, fall apart quickly. They rot and decay. Bacteria get in there and decompose the fish, and it's not too many days before scales start falling off. One thing I noticed right away is that dead fish oftentimes don't float, they sink. And then as gases start to build up in their belly and stuff like that, then they float. And then the gases sometimes build up to such an extent as their belly pops, and then they'll sink again. And I actually found a number of fossil fish in the Green River Formation in Wyoming that displayed some of those characteristics. So I learned a lot from my experiments about how to interpret the fossils. But it didn't matter if I had deep water, shallow water, water with oxygen, water without oxygen, salt water, fresh water, cold water, warm water. It didn't matter what I did. The fish rot and decay. Did you ever think about why you put food in your refrigerator or your freezer? What's the purpose? Yeah, it's to retard the decay process, right? And so that's the only thing that really retarded the decay is I had some fish down in the walk-in cooler downstairs. And that's the only thing that retarded the decay process. It turns out that it really doesn't matter the organism. Whether it be a fish or an insect or a plant or a crab. People have done experiments with turtles, with birds, all kinds of things. People have done experiments with, paleontologists have done experiments with to see how the decay process takes place. My advisor was studying another deposit in Wyoming that had fossil turtles. Leonard Brand, the same guy that did the footprints in the Coconina. He was studying this deposit with fossil turtles, and none of the turtles had heads. So perfectly preserved turtle, with the limbs and whatnot, but their heads were gone.
No shell.
No, it had a shell. Everything was there except the head.
I'm saying the head didn't have a shell.
Right. And so what in the world happened? Well, he did some experiments with turtles and found out they floated just like the fish do, but the head would kind of droop down, and apparently the muscles and linkage, hooking it all together, that's where it got weakest, and the heads fell off. So that's, he figured out, at least came up with a good explanation, a reasonable explanation as to why these turtles didn't have heads. And so it turns out, no matter what organism that you have, if you don't cover it up quickly, if you don't bury it, it's going to rot and decay. And so whenever we find a fossil in a rock, It doesn't matter the kind of fossil. Whenever you find a fossil, it means that that fossil was made quickly. It had to be buried before it had the opportunity to decompose. Does that make sense?
That's absolutely right.
And so, and again, it doesn't matter if you have the kind of organisms I've been talking about, even if you have bone or hard shell. Experiments have been done with bones and hard shells as well. And all those kinds of things decompose rather quickly. There are a famous set of experiments carried out with whales, dead whales. And the scientists took a dead whale, they towed it out to the ocean, sank it down to the ocean floor, and figured they'd come back in a few months to see what had happened to it. And they couldn't find it. They had marked it really well and everything. They couldn't find it to investigate it. So the next one they got, they actually put a camera on it, a time-lapse camera on the seafloor to watch what happened. And they were amazed at the marine life that came and just swarmed on it all throughout the ocean floor and just decomposed that carcass within a matter of weeks because it's a nutrient source down there in the ocean. And not just the flesh, but the bones as well. Organisms would come and drill into the bones and consume the nutrients that are in the bones. So even when we find, like dinosaurs or other types of bones in the rock record, they must have been buried quickly in order to be preserved. And guess what? You see this stack of rocks that we have here? All these rocks have fossils in them, and we're going to look at some in just a few minutes. But all these rocks have fossils. So what does that tell you about each one of these rock layers with fossils in them?
Quick.
Had to be made fast, and we have really good evidence that all these rocks were made underwater as well. Okay. All right. So my professor, Steve Austin, used to be at Institute for Creation Research. He's over in Pennsylvania now. But one time somebody challenged him, and he said, you guys have been doing really good work in Grand Canyon, but you're never going to be able to explain how the Redwall limestone formed. So that's what we have right here. This is the Redwall. Look across the river, you see this red wall right here. That's the Redwall limestone, one of the easiest formations to pick out in the Grand Canyon. And if you're on the rim, the Redwall typically sits about halfway down into the Grand Canyon. So we're about halfway down into that stack of rocks in the canyon. But this geologist challenged Steve Austin and said, you're never going to be able to explain how the Redwall formed because everybody knows that it formed in a calm and placid sea. And one thing this guy didn't know is that you never challenge Dr. Austin because he's gonna come up with an answer. And so it's true. A lot of people believe that this limestone was formed very slowly. When geologists go to school and learn about rock formation and stuff like that, we're often either take a field trip a lot of times, or we're taught in the classroom or the lab places where rocks are forming today. And so this is a limestone. So if you want to study limestones, you go to a place like the Bahamas. Nice warm water, lots of corals and reefs and stuff like that, and that's supposed to be the typical environment for limestone formation. And so because we see it forming slow today, just a little bit of lime building up over time, that's the assumption that's made when you find limestone in the rock record. That's how you're supposed to interpret it. In fact, that's how most rock interpretation works, is that you're aware of where something similar forms in today's environment, and therefore, when you see it in the rock record, you think the same thing. It's called uniformitarianism. The present processes and rates and so forth, that's the key to the past. So that's how geologists are trained. That's how I was trained. And so Steve Austin started to work on the Redwall, and one of the more famous fossil deposits in the Redwall, and it was known at the time, was called the Whitmore nautiloid bed. Now it's not named Whitmore after me, but it's named Whitmore after the canyon that we're actually going to fly out of. So when we get on the helicopter and fly up to Barton Ranch, that ranch is in Whitmore Canyon. And when you name a rock layer or a bed within a rock layer, you name it after a geographic location. You're not allowed to name it after yourself or something like that. So it's called Whitmore because it's located in Whitmore Canyon. Whitmore Canyon, Whitmore Wash, was named by John Wesley Powell after a guy named Whitmore, James Montgomery Whitmore, that used to live in that canyon, and he was murdered by Indians. Indians took his sheep and cattle. He went out to get them and get them back, and he was murdered in the process. So Powell named that canyon down there after him. But this Whitmore nautiloid bed, that's the first place where this bed was described. And since it was first described, it's found out to be quite extensive. And so a nautiloid is a squid. So here's what a squid looks like, and like an octopus, squid has tentacles, but instead of 8 tentacles, they have 10. Okay, and so I've got him out here with his tentacles. They also have a really big eye. These things are really good swimmers, and they're good hunters as well. They go deep down in the ocean, and so they have that big eye to take in lots of light so they can see what they're doing, I suppose. But these squid, these nautiloids, had straight shells. So their shell was kind of like a giant ice cream cone. So if you can imagine a giant pointed ice cream cone, the organism lived inside of that shell, and its head and its tentacles came out the other end. And these organisms, they had all these chambers inside their shell. They actually had an organ that could either put gas in the chambers or take gas out of the chambers, and that way they could either rise in the water column or sink in the water column just to the right level, so they could hunt at that particular level. They wouldn't have to spend a lot of energy swimming up or swimming back down. They could hang out at the same depth in the ocean. But we do have one species of this left today. You've probably seen in an aquarium or zoo the chambered nautilus. They have a coiled shell. They're similar type of organism to this. So in this Whitmore nautiloid bed, here's what the rock looks like, and we're actually going to go downstream in just a few minutes here and look at this. The nautiloids are buried right in the middle of this nautiloid bed. So the nautiloid bed's not very thick. It's about 7 or 8 feet thick or so. And the nautiloids are buried right in the middle of it. And nautiloids aren't the only thing in there. There's corals and some other things you occasionally find in there. But the thing that stands out are these nautiloids, and they're big. Some of these things were 6, 8 feet long. The ones you guys are seeing will be about 1 foot to 2 feet long, so they're big. And sometimes they're really big around as well. You guys are going to see the end of one that's literally that big around. So that thing is probably 8 feet long. Okay. Some of these nautiloids got up to be the size of telephone poles. Really big. And the interesting thing is they're buried right in the middle of this nautiloid bed. The Whitmore nautiloid bed is right at the bottom of the Redwall. So the Redwall, as we go downstream a little bit, we'll see it sitting on top of Nuov Formation. But nautiloid bed is always right at the bottom of the Redwall. And then right on top of the nautiloid bed is this, right here. See all these stripes in here? We went through Tiger Wash just upstream a ways. And that's why they call it Tiger Wash, because it has all these tiger stripes in it. Okay? And these are alternating layers of chert and limestone, actually dolomite, and is an interesting formation. It's called the Thunder Springs member of the Redwall. And so anyway, Austin gets this challenge, and so he says, okay, I'm going to go to this most famous unit of the Redwall, and I'm going to start studying these nautiloids. And he came down here with his Brunton compass, the same thing that I used to measure strikes and dips of the crossbeds in the Coconino. Geologists have a lot of uses for the Brunton compass to measure various azimuths and orientations and stuff like that. He began to measure the orientations of the nautiloids in the nautiloid bed. And we're going to go to one of the places where he measured those orientations. Now, how many of you have ever been canoeing or kayaking down a river? So when you get trees in the river, a tree is a long object, right? And oftentimes the trees either will parallel the current or they'll be perpendicular to the current, right? In other words, when a current goes down a river, it will take long objects like a tree, and it will orient them either perpendicular or parallel to the current. There's not too many that are at an angle. Sometimes you find that. But in the fossil record, the same thing happens. When you have a current that's carrying long objects, those long objects will get oriented within the current. And so Austin started measuring all the orientations of these nautiloids with his compass. And he had some helpers as well. And one of the first spots that he did that, one of the first places in the Grand Canyon where it shows up, is the place we're going to go. And then there's another place just down beyond that called Nautiloid Canyon, which there's a slot canyon that's cut right down into the nautiloid bed, and so all these, you can see all the polished nautiloids right in the bottom of that canyon as well. But one of the places he started measuring is one of the places we're going to go look. And it's right next to the river, a real easy site to get to. And he found dozens of places along the Colorado River, and even out into Nevada, so toward Las Vegas. He found other places where this nautiloid bed shows up, and measured all the orientations of these nautiloids. There's another place called Garden Wash, south of Mesquite, that he went to. I've taken my students there before, and we've looked at the nautiloids there. But this nautiloid bed shows up all over the place. And it turns out it's about 300 miles long. And everywhere where you find the nautiloid, you find the Whitmore nautiloid bed, you find nautiloids in it. And based on the density of the nautiloids, it's estimated there's at least 6 billion, that's billion with a B, nautiloids buried in this layer. All right, and you looked at all the orientations, and guess what? They have a preferred direction. And what that means, these things weren't dying and falling down to the ocean floor in a random pattern like they would in a calm and placid sea, right? These things were being buried alive in the current that I'm going to explain in just a moment. So the first step, the first key to figuring something out here was recognizing that these things are not randomly oriented. They have a preferred orientation, and when you figure out that preferred orientation, you can figure out which way the current is moving. And so Austin comes up with this hypothesis to explain this nautiloid bed over here. And the other thing I didn't mention, these red lines that I've drawn in there, he didn't know what these were at first, but there's these vertical tubes that are often filled with calcite. Sometimes they're hollow, but oftentimes they're filled with calcite, and they're vertical, and they just occur in the nautiloid bed themselves. They don't go up into other formations. And so he didn't know what those were either, but he eventually figured that out in his model. So what he came up with is that he hypothesized that we had a large high-density current that flowed on the bottom of the ocean floor. This current would have been kind of like the density of cement, wet cement. If you've ever mixed cement before, it would have been kind of like that. And believe it or not, this is not moving slowly along the bottom of the ocean. This is actually moving like an airplane wing. It probably has water underneath of it as well as on top. And as this high density current moved along, it actually swept up nautiloids that were swimming in the water column. It swept up and incorporated nautiloids in it while it was moving along the bottom. And so geographically, this would have been like from Colorado all the way to California that this process is happening. Okay, during the flood, this bed is moving along, catching up these nautiloids. And then as you get a current moving this way, for every action there's an equal and opposite reaction, right? If you got a current moving this way, it's going to make another current coming back the other way, a countercurrent. And Austin suggested that's what all this is. All this Thunder Springs member is the result of the countercurrent that's happening as this nautiloid bed gets laid down. All right, so he comes up with this great hypothesis. And I watched him present this at a Geological Society of America meeting. And word got out. Oh, this creationist, the worst kind of creationist, the young earth creationist, is going to present this crazy idea about the nautiloid bed in Grand Canyon. And word got out at the conference. So these conferences usually have 6,000 to 8,000 geologists at them. And word got out, and the room was actually absolutely packed. I mean, there was 300 chairs in there, but I bet there were 600 people in the room. Or there are people sitting on the floor in the aisles, even up on the stage where he was talking and so on. And he gave his presentation, and the time ended. And is there any questions? And the room was absolutely silent. Nobody could come up with an explanation to contradict what he had described, because his mechanism, and it's a model, it's a hypothesis, but his hypothesis explained perfectly the features of this nautiloid bed. And we've done experiments in the flume like this, and all these things always end up right in the middle of the deposit for some reason. It's a physics reason. But the other thing that happens, the hypothesis is this bed was deposited so quickly, and the other stuff was put on it, on top of it so fast that it pressed down on it. And have you ever pressed down on a wet sponge? What happens if you press down on a wet sponge? The water shoots out, right? And so these red lines that I've drawn in there, those are hypothesized to be water escape tubes. And so he put all this together and presented it at the conference, and nobody was able to contradict him. Now, whether his model was right, I don't know. I think it's a tremendous model, but I think what he was able to demonstrate is that the Whitmore nautiloid bed was not made in a calm and placid sea. And so, here's another great Grand Canyon story that shows that when a creationist does good scientific work, and a creationist can do good scientific work, we can often find explanations that fit really, really well within a flood model. In fact, now there's no other explanation for how the nautiloid bed can be deposited except for quickly. With these features that he found and identified, you can't come up with a slow model for the nautiloid bed. You understand what I mean? It's not an option anymore with those kinds of features. So just a great story in Grand Canyon geology. Another one. We'll talk about some more as we go downstream. But
so did he do this a while ago that people have been working at?
Yeah, it's been about 20 years since he's done this research. But a great piece of research that he did. He's done some other things too. He's done some work in Israel. He's done a lot of work at Mount St. Helens and some other places too. But really great story. Questions? Yes?
Are nautiloids found in any Ohio?
Yeah, you can. In Ohio, I often collect fossils down near Waynesville, Ohio, at Cedar Creek State Park, and they have nautiloids there. And there's lots of other layers that you can find them in.
So you can find them, and these are low level. You can find them in higher layers too, right?
Yes, yes, and they're still alive today.
Yeah.
Yeah.
They look just the same too.
Yeah, this species is not living anymore, but the coiled nautilus is.
Oh, yeah.
Yeah. Yes.
Other animals can swim out, but they had to rise and fall in that certain time, or why the density of the nautilus in this?
Yeah, I think squid tend to swim in schools, and so this density current probably hit a school of squid that was swimming around.
And are there other creatures that are found in the areas?
There's some corals and a few other odds and ends, but nautiloids are definitely the most abundant.
So other animals could get out fast enough that this would.
Maybe, but things like a coral can't move. Like you can find some big coral heads and stuff like that in there. Yeah.
And have there been any other theories for the nautilus that's post presentation?
No, the first theory was, calm and placid sea, but Austin showed that can't be the case, and nobody else has proposed anything different. Yeah. And this is one of the most famous formations in Grand Canyon. There's a lot of Grand Canyon geologists working out there. No other explanation to this point.
And some of those are not creationists that are trying to do something with the nautiloids.
I don't know that anybody else has tried, so it'd be interesting to see what they find out when they do. So,
Thank you.
yes. All right, now.
Oh, I think the question.
Yeah.
So I went a little too fast for you. You said it was the current and the counter current
Yep.
that accounts for these stripes?
Yeah. So these are alternating bands of chert and dolomite, which is a high magnesium form of limestone, and it's a combination of a physical and chemical process it's taking there, probably in hot water, but probably hot water, yeah, based on some of the chemistry that's in there. But yeah, I'm not going to go into the physics and that, but yeah, with this group.
When you say break out
Yeah, I think this nautiloid bed was at any one location was probably made within minutes, and then I don't know, maybe less than a day for the rest of this Thunder Springs number. We're talking about rapid processes now. As you look across the canyon over there, especially above the Redwall, and you see some of the supai up there, you see lots of layers in there, right? This is a good model to explain how we get these nice flat layers that extend for miles and miles and miles. Don't think that these layers were just simply settling through the floodwater. A lot of people like to do this homeschool experiment where you take a jar of mud and gravel and shake it all up and sit it on the counter and watch it settle. The big stuff settles out first and the other stuff settles out over days. Don't think that layers were formed like that during the flood. We have other ways to make multiple layers very, very quickly through catastrophic processes. The flood was not a giant washing machine that then got turned off when all the layers got made. No, these layers were made during the midst of this catastrophe, and probably made by things that were flowing along the bottom of the ocean floor, just like this.
What is your estimate of how many days it took to make the Grand Canyon? A lot of runoff, wasn't it?
Well, to make the
to do what we have here.
I want to be clear of what you're asking. To make the rocks of the Grand Canyon, or to make the gorge of the Grand Canyon?
Well, I mean the whole thing, the gorge, I guess.
Yeah, we'll talk about that later.
Okay.
We need to find a good lunch stop to talk about that.
One other question though. This what we're seeing. There are things like this all over the world, right? Not just here.
That's right. Yes.
It's a global flood.
This is a global flood. And by the way, the Redwall, we can trace this all the way into the Black Hills of South Dakota. If you've been up that way, the Madison limestone, the Pahasapa limestone, same limestone up there. How many of you have been to Mammoth Cave in Kentucky? Same rock. And this rock also outcrops in the Alps. and throughout places throughout Europe. Does that give you an idea of the global scale of
Yeah.
the flood? Yeah. We're going to look at another formation. Probably we'll see it first tomorrow. That probably is a worldwide formation. Like, I mean, this one goes pretty far too, but we can trace it to peat sandstone even farther. So this is a worldwide flood. This is not some local thing that's happening. And if you get a limestone layer, this limestone layer is on top of a continent, right? And if it's the same layer that goes over into Europe, North America and Europe had to be underwater at the same time, right, to make this. So it's a worldwide flood that's making worldwide sedimentary deposits. And by the way, you guys are on land, right? What are marine fossils doing and rocks that are on the land? What are marine rocks doing on the land? What's the best explanation for marine rocks on land? The flood, and that's one of the best evidences for a flood. Now, I'm going to give you guys a few minutes to actually look for some fossils in these boulders behind me. I haven't found any nautiloids. There may be some there, but there are things called crinoids in here. Crinoids look like a stack of coins. In cross section, they're just round. Sometimes they'll have a little star in the middle. So there's crinoid fossils back here. There's bryozoans. The bryozoans kind of look like lace. Sometimes they're called lace corals. They're not really a coral, but they look like a real fine lace. There's some brachiopods back here, but just scour among these boulders and see what you can find. If you find something, holler and let some other people see it too. I won't tell you where they are. I want you guys to look.
That's
All right.
like a stressor.
Isn't there